Hello dear students. So in the last class we had discussed the wave propagation in lossy dielectric medium. Okay. So which topic we had discussed? We had discussed the wave propagation in lossy dielectric medium. Okay. This we had discussed. Okay. So in the course of derivation we had seen one variable. Okay. So what we had defined it? We had defined it propagation constant. So this we will elaborate more now. Okay, today in today's lecture we will elaborate this. So this gamma square equals to, it is j omega mu into sigma plus j omega epsilon. Okay, this is your gamma square. Okay, and what is gamma? Where this gamma is the propagation constant. Okay, propagation constant. Okay, now we had discussed that if this gamma is what, this is complex, then it would have the real and imaginary parts. Okay, so then this gamma can be represented as alpha plus j beta. Okay, this we had discussed, where alpha is what, where alpha is the attenuation constant. Alpha is the attenuation constant. Okay, and it is measured in Nipper per meter. Nipper per meter. And what is beta? Beta is the phase constant. This we have discussed earlier also. The beta is the phase constant. Okay, and this is measured in radian per meter. Okay. So since this gamma square equal to j omega mu sigma plus j omega epsilon. Okay. So it can be written as gamma equals to j omega and root over of this mu epsilon, okay, and root over of 1 minus j sigma upon this omega into epsilon. Okay, what we have done, just this is the gamma square, so gamma will be what, root over of this. Okay, and from inside we have multiplied these terms. Okay, and then we have taken this j omega e common. Okay, j omega e if we take common, then we will get this formula. Okay, now this gamma can be, gamma can be separated, okay, into alpha and beta, matlab real and imaginary terms, alpha and beta. So what will be this gamma square now? So gamma square is equal to, it is alpha plus j beta, we can represent it. So alpha plus j beta, it is whole square. Okay, and what is this? This value is j omega mu sigma plus j omega epsilon. Okay, so that we can write j omega mu and into sigma plus j omega epsilon. Okay, now if we use one identity, so alpha plus j beta whole square, what it will be? A plus b whole square entity, the simple entity that will use alpha a square plus b square plus 2ab, we already know. So what is in place of this alpha plus j beta whole square, what we can write? We can write this alpha square plus j square beta square, okay, and plus j into 2 times this alpha beta, okay, and this can be written as what? This here also will multiply and separate the real and imaginary terms, okay. So here it is sigma omega mu, sorry, j omega mu sigma plus this j square omega square and mu and epsilon, okay. Now we know that what is the value of j square, okay, iota square, it is -1. So alpha square minus beta square, this will be your one term, this will be your real term, okay, and this j, the term containing j, will be your imaginary term. So it is j 2 alpha beta. So if you will compare this with any complex number, then this will be the real part and this will be the imaginary part. So here also this j square will be how much? -1. So this omega square mu and epsilon, this will be the real term, minus omega square mu epsilon, this will be the real term, and this and plus j omega mu sigma, okay, this is your imaginary term. So we can compare the real and imaginary term on both the sides, okay. So we can compare the real and imaginary terms on the both the sides. So now comparing the real and comparing the real and imaginary terms on both the sides. So on comparison, what we will obtain? We can compare the real part with the real part. We can compare the imaginary part with the imaginary part. Okay. So the real part on the left hand side is alpha square minus beta square, and on the right hand side that was minus omega square mu epsilon. So we can we have compared this. Okay. So put it like equation 1. Okay. And this 2 alpha beta, except this j term we will compare, that is your imaginary term. So 2 alpha beta on the left hand side will be compared with this omega mu sigma, okay, and this is your second equation. Fine. Now if we solve this, so solving equations 1 and 2, we get the following equation, okay, that I had shown in the last class also, that alpha will be equal to omega root over of mu epsilon upon 2, okay, inside bracket it is root over 1 plus sigma upon omega epsilon square and minus 1, okay, and your beta will be omega root over this mu epsilon upon 2, and this root over of 1 plus sigma upon omega epsilon square and minus 1, okay. So this is your alpha and beta, only the difference is minus and plus 1, here it is plus 1, okay. So only difference is here it is minus 1 and it is plus 1, okay. So alpha and beta, after solving equation 1 and 2, we can get like this, okay. Now we have some special cases, okay, we have some special cases here. So your case 1 is So one case is in a lossless dielectric, that was lossy dielectric, okay, and in a lossless dielectric, these equations are for lossy dielectric, and now I am considering for lossless dielectric where there is no loss, okay. So for lossless dielectric, what are the assumptions? So this sigma is very much lesser than this omega epsilon, okay. So this sigma is means not exactly equal to 0 but near to 0, because it is very small as compared to this omega epsilon. Epsilon equals to what? Epsilon 0, epsilon r, okay, and your mu is also mu 0, mu r, okay. So what will happen if we put these values? So what will happen here? So if we will put these values here, okay, so this sigma is 0, let's say. So 1 minus this sigma is 0, then this term will be 0, okay, and 1 root over of 1 means 1, 1 minus 1 is 0. So alpha is what? So after putting these conditions in this equation, okay, so alpha will be 0, okay, and your beta will be equal to how much? Omega, and this 1 plus 1 2, okay. If you put sigma equal to 0, so this root over of 1 and plus 1 2 and 2 will get cancelled out, so omega upon root over mu epsilon, okay, omega into mu epsilon. So these are the conditions which we obtain for this lossless dielectric, okay, and these conditions were for what? Lossy dielectric. That in the beginning of the discussion I had written the topic, okay, lossy dielectric, okay. Now we will consider the case 2 and case 3 for the free space and for the good conductor, okay. So now the case 2, so now the case 2 is for free space, okay. Case 2 is that in free space, okay. So in free space what will happen? What are the considerations? Sigma equal to 0, epsilon equals to epsilon 0, okay, and your mu equals to mu 0, okay. These are the considerations for free space. For free space, conductivity is 0, your sigma is equal to, sorry, epsilon, permittivity is equal to absolute, so permittivity will be equal to this epsilon 0 and mu will be equal to mu 0. This is the consideration for the free space. So in this case, if we put these values in the expression for alpha and beta that we had derived for the lossy dielectric condition, then what will happen? So the alpha will be simply 0 because sigma is 0, okay. Epsilon naught and mu naught, that will put, okay, and your beta will be equal to omega root over of this mu 0 epsilon 0, okay. So if you remember the condition, 1 upon this mu 0 epsilon 0 root over is equal to the speed of light. So if we will put this, then we will get omega upon c, okay. So this is the condition for free space, okay. And the case 3 is the case 3 is in a good conductor. If the medium is a good conductor, then what are the considerations? Okay, so a perfect or good conductor is one in which sigma is very much greater than omega epsilon. Okay, so a perfect or a good conductor is the one in which this sigma is greater than omega epsilon. Okay, so that this sigma upon omega epsilon is very much larger than 1. So in this case, it is a perfect conductor. So the considerations are this sigma, the conductivity is infinite. Okay, epsilon equals to epsilon 0 and mu equals to mu 0 mu r. Okay, so these are the considerations, and on the basis of this, if you put these conditions into the expression of alpha and beta that we derived in the beginning for the lossy dielectric medium, then we will get this alpha equals to and beta both are equal, and that will be equal to this omega mu sigma upon 2. So this is the condition which we can obtain by putting this. Okay, so these are the different special cases, okay, that we have discussed here. Okay, and the next topic of discussion is the skin depth, which is a measure of the depth to which an electromagnetic wave can penetrate the medium. Okay.